Hello, this is Mr. White, and this video is on increasing/decreasing intervals and the first derivative test. So here are the two exercises for this video. All right, let's go ahead and find the critical numbers of f, if any, and find the intervals in which the function's increasing or decreasing, and then ultimately find all the relative minima and maxima, aka extrema. So, to find the critical numbers, we take the first derivative of the function, which in this case is going to be 3x squared minus 12x, and then plus 0, which I won't bother to write. And remember, we set it equal to 0 or undefined. Now, in this case, we're dealing with a polynomial here. Polynomials are continuous and they're differentiable. You'll never get the undefined case, but it's still just a good idea to write it anyway, just to stay in the habit that we, in general, will look for undefined cases as well. So let's go ahead and solve that. Let's factor out the greatest common factor, which is 3x. And that means that inside this parentheses goes an x minus 4. And that means that x equals 0 or x equals 4. And these are our critical numbers. What's the significance of critical numbers? Well, all extrema occur at critical numbers. And likewise, any time where you have an increasing or decreasing interval, those intervals start and stop at critical numbers. Not counting infinity and negative infinity, of course. Okay, so we got the critical numbers. Now we're to find the open intervals on which the function is increasing or decreasing. And that goes hand in hand with finding the extrema. So we're going to be working on both of those tasks simultaneously here. And remember how we do that. We start with a table. And our textbook suggests that you set it up as a table, which I think is a good idea. And we start with intervals. And to set those intervals, picture a number line. Picture a number line going from negative infinity to positive infinity. And then picture your critical numbers on that number line. So let's say 0 is here and 4 was here. So our first interval is going to be this stretch, which is from negative infinity to 0. Our next stretch, or our next interval is going to be this stretch, which would be 0 to 4. And then finally, our last interval would be for this stretch right here, which is from 4 to infinity. Okay, and what comes next in the table? Our book suggests a test value. So just pick some number that you anticipate will be easy to work with that is somewhere on that interval. So what's a number that is somewhere on this open interval? And I emphasize open just to say that I can't pick 0 itself. Can't pick the endpoints itself. So let's just pick negative 1. Again, it could be any number on that interval. And likewise, for this second interval, let's put 2 in there. I could have used 1 or 3 or any number, whole number or not, on that interval. And finally, let's put a 5 there on the interval from 4 to infinity. All right, and the purpose of that test value is to help us figure out the sign of f prime. And remember, f prime is what's going to tell us whether this graph is increasing or decreasing. And we know that whatever it's doing on this interval, increasing or decreasing, whatever it's doing at negative 1, it's doing over that entire interval. So if it's increasing at negative 1, we know it's increasing over the entire interval. Likewise with decreasing, of course. So let's shrink this just enough so that I can see the derivative on the screen at the same time. There we go. And again, I'm looking up here. Here's where our derivative is. And again, I actually like this form of the derivative better. That's the one that's going to make the sign easier to see. So if I'm looking at this test value of negative 1, and I imagine plugging in a negative 1 here and a negative 1 here, I see that I have a positive number times a negative number times a negative number. Oops, excuse me, I should say times a negative number there. So positive times negative will give me positive. Remember, I don't care about the actual value, the actual number. I only care about the sign of f prime. So let's plug in a number 2 there. So here is a 3 times positive 2 times 2 minus 4. That's going to be positive, positive times a negative number. Positive, positive, negative. That's going to be a negative result. And finally, plug in a 5 here. I'll get positive number times a positive number times another positive number. That gives me positive. As I'm sure I've warned you in class, it's very tempting. Once you get the first sign, it's very tempting to just keep flip-flopping and alternating. So positive, negative, positive, negative, positive, negative. But beware, while that may work 9 out of 10 times, every so often you'll get, like a positive followed by another positive. So you can't assume. You've got to verify through that step the sign of each f prime on each interval. Okay, so finally in the table is our conclusion. And what does positive mean? Again, keep in mind that we're saying that f prime is positive. That means that f is increasing. Whenever the derivative is positive, that means f is increasing. And that means that when it's negative, when the derivative is negative, f is decreasing, and then back to increasing again. And I always like to just draw a little sketch underneath, just so I can very visually see that. I like to draw a positive or an increasing curve followed by a decreasing curve, and then finally increasing in this case. And that helps me visually see that we've got a maximum here, top of a mountain, and then a bottom of a valley here. And that all makes sense, because to some degree we already knew that when we're dealing with these kinds of x cubed function, we already knew that when this had a positive coefficient here, you already know on some level that that looks like that typically, right? But we're just confirming it here. Okay, so we were to find the intervals on which the function is increasing or decreasing. So as a formality, I'll say increasing on, and I'll just kind of copy this here, negative infinity to 0, decreasing from 0 to 4, on 0 to 4, and then increasing again on the interval from 4 to infinity. That's part of my answer, the conclusion there. And then finally, we were to find all the extrema, right? So where did this extreme occur? We see that that is a local max. And we see that this is going to be a local min. And remember, that occurred at these critical numbers, 0, which divided this interval here, and 4, which divided these intervals here. So we'll put the local max is at 0, and the local min is going to be at 4, at an x value of 4. And finally, we just need to find out what the y values are. And I go to my original equation, and if I were to plug in f of 0 equals 0 minus 6 times 0 plus 15, clearly I would get a 15 here. And if I were to plug in a 4 here, I would get a, negative 17 here. And clearly that could be confirmed, all confirmed by calculator. But that is our answer. We found the intervals of increasing, decreasing, and we also found the extrema. All right, let's go on to the second exercise. Our task is the same. Find the critical numbers, open intervals on which the function increases and decreases, and find the minima and maxima. Now, if you're looking at this function and you don't have as much of an intuitive sense as to what this is going to look like, I don't blame you. But that's really what our activities now are building up to, is developing this set of skills that will help us figure out what a function looks like without using a calculator. So between finding extrema and increasing, decreasing intervals, we can start to get a sense of what it looks like. We already have some clues. We can tell that there's a vertical asymptote at x equals -2, right? We could do limits as x approaches infinity and negative infinity, and we can find the horizontal asymptote. We can find x-intercepts, y-intercepts, and such. But let's go ahead and start with our critical numbers here. Now, I'm looking at this and wondering if there's any fancy algebra I can do to make my job easier. The ideal case, or the easiest thing, would be, let's say that this top factored into x plus 2 times some other binomial factor, and then we could take that and cross out the x plus 2 on the top and bottom. So be on the lookout for things like that. Sometimes that does happen, but it doesn't look like it's going to happen here. The top doesn't even really factor across integers, does it? So let's just go ahead and use our quotient rule. F prime of x equals bottom times derivative of top minus top times derivative of bottom all over bottom squared. All right, let's distribute that out. Remember, in general, we're going to leave the bottom alone, leave it in factored form, but the top will distribute everything out, combine like terms, and then factor it again if possible. So if I FOIL that out, I'll get 2x squared minus 3x plus 4x. That's going to be plus x minus 6. And then don't forget to distribute the negative on this part. So we'll get minus x squared plus 3x minus 6 all over x plus 2 squared. We'll combine our like terms. So the 2x squared and the minus x squared give us x squared. Plus x plus 3x gives us plus 4x. Minus 6 gives us minus 12. All over x plus 2 squared. And we check to see if the top is factorable, and it turns out it is. We're going to get, let's see, x plus 6, x minus 2, all over x plus 2 squared. And let's set that equal to 0 or undefined. And we'll see that our solutions are, from that factor, we get x equals negative 6. From this factor, we get x equals positive 2. And those are what are going to make the derivative equal to 0, right? When the numerator is 0, the whole fraction will be 0. Now, what's going to make the whole fraction undefined? That's when this denominator is equal to 0. That's what's going to give us undefined. So we see that x equals negative 2 will do the trick there. Okay, so we are first tasked with finding critical numbers. Critical numbers. I should point out, though, that this is, again, one of those little technicalities we have to be aware of. Technically, the critical numbers are just those first two. Now, we don't want to completely cross out the last one, the x equals negative 2, but only the first two are critical numbers. And do you recall why? Well, let's scroll back to the top and look at our original function. And remember that critical numbers have to be in the domain of the original function. Notice x equals negative 2 would not give us a real output. In fact, that's where we said our vertical asymptote would be. So we want to observe that x equals negative 2 in our next step for making intervals, but we will not call it a critical number. We'll maybe make a note that it's a discontinuity there. And the reason why we still want to acknowledge it is because when you think about the fact that we're trying to find increasing, decreasing intervals, a discontinuity could definitely be a point at which the function changes from, let's say, decreasing to increasing. So that definitely could be a part or a point where the function changes behavior, so that's why we don't want to ignore it. So let's go ahead and figure out what our intervals are going to be. And again, I typically like to start with the number line. Let's say that this is negative 6, and this is going to be our negative 2, and then we'll have the positive 2 here, and of course we'll have negative infinity and positive infinity here. So remember on our table, our first step is the interval. And so our first interval is from negative infinity to negative 6. Our next interval will be from -6 to -2. Our next interval will be from -2 to 2. And finally, our last interval will be from 2 to infinity. All right, we follow up with the test value. Again, just some number in that interval. Let's say, how about -7? How about -4? Say 0, and let's say 4. Just to keep them all even. Well, I guess they weren't all even, were they? The first one was 7, so we'll put a 3. I don't know why I'm nitpicking over that. That doesn't really matter, does it? So do you remember what comes next? Sine of f prime. So if I scroll back up and I look for the most user-friendly version of my f prime I can find, again, the fully factored form is the one that I would argue is the best one. So let's take that fully factored form, drag it down here. That's our f prime. And let's evaluate, oops, somehow missed out a parentheses there. And let's evaluate the sine of f prime for those various values, those various test values. So I try out the -7, and I'm going to get a negative number, another negative number, and since we're being squared down here, that's going to be positive. So negative times negative over positive will give me positive, right? Our next test value is going to be -4. Plug in a -4 there. And again, I caution you, avoid the temptation of just doing negative, positive, negative, of just assuming that they alternate all the time. So -4 plus 6, that'll be a positive number, followed by a negative number all over positive number squared. Notice the bottom's always going to be positive. So that will be negative. It will alternate here. 0, that'll be 0, 0, 0. We still be positive, negative, positive. And so as I warned again, it doesn't always alternate. We got a negative again. And finally, test value 3. We have positive, 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 positive overall. So as far as what our function looks like, we can start to get a sense here. We know that the function increases due to this positive f prime. We know that it must hit a local maximum and then decrease. And remember how we said that there's a vertical asymptote at -2, right? So we get a sense as to why we have a negative followed by a negative. There's a vertical asymptote here, and then following that vertical asymptote, it's decreasing again. So that tells us that it must be riding downward along the vertical asymptote, followed by positive. Let me draw it a little more like this. Followed by increasing, right? So that's where it would then swing upward. Now we still don't have a real sense of where these branches are in relation to each other, up and down, but we're just developing the picture here. And we can at least conclusively say by the first derivative test that this is our local maximum. And that occurred at -6, x equals -6. We can say that this is going to be our local minimum. And that occurs at x equals 2. And if I bring my original function back up here, I could plug in the x values, the -6 for example, into this function, and I would get my y value, which turns out to be -15. And same deal with the 2 over here. I could plug that in and get a +1 there. And those are our extrema. And since we have the means, we might as well check it via graphing calculator. Here we go. And Again, we could use the calculator using trace or calc max, calc min to verify that that local max occurred at -6, -15, and that that local min occurred at 2, 1. And notice that the shape is pretty much what we anticipated too, as far as how this would look in relation to that vertical asymptote.